Here are some examples in finding the first and second derivatives of parametric functions. Welcome to differential calculus. The first pair of parametric equations for differentiation has x is equal to 4 sine of t and y as 2 cosine of t. First, take the derivative of each variable with respect to t. dx all over dt is 4 times the derivative of sine t, which turns out as 4 times cosine of t with dt all over dt, which is taken as 1. So the simplified dx upon dt is 4 cosine of t. Y's derivative starts with 2 times the derivative of cosine t. So dy all over dt is 2 times negative sine of t with dt all over dt, again taken as 1. So dy upon dt is negative 2 times sine of t. Having both derivatives, we move on to take dy all over dx, and that is to divide dy all over dt by dx all over dt, which is negative 2 sine t divided by 4 cosine of t, simplified as negative sine t all over twice of cosine t. Again, note that sine all over cosine is tangent, giving dy all over dx as negative half of tangent t. Moving on to the second derivative of the parametric pair, we continue by taking the derivative of the previously solved first derivative with respect to t. So we get negative 1/2 of the derivative of tangent t, which is secant squared of t, giving the second derivative of y with respect to dt dx as negative half of secant squared t. From this point, we take out dt from the equation, and we do that by multiplying everything by dt all over dx. Take note that we have already solved dx all over dt earlier, which turned out as cosine of t. Take its reciprocal to have dt all over dx, with 1 all over 4 cosine of t. If we use trigonometric identities, we can simplify this as secant of t, making dt all over dx as secant t all over 4. Now, the second derivative of y with respect to x is negative 1/2 of secant squared t multiplied by secant t all over 4, which is reduced further as negative 8ths of secant cubed t. Example 2 has the pair x is equal to negative root of t plus 1 and y is equal to the root of 3t. Start by taking the derivatives with respect to t. dx dt is taken as the derivative of negative root of t plus 1, where we can transform the radical sign into a fractional exponent. With this, we use the power rule, giving dx all over dt as negative of the exponent 1/2 times the quantity of t plus 1 raised to negative 1/2, and this is multiplied by the derivative of t and the derivative of 1, which turn out as 1 and 0. So the simplified dx all over dt is negative of 1 upon 2 times the root of t plus 1. For y, we do the same procedure, that is to take the derivative of root of 3t taken as 3t raised to 1/2 in its exponential form. Using power rule again, we have dy all over dt as half of 3t raised to negative 1/2, then multiply this by 3 times dt all over dt taken as 1. So dy all over dt is 3 all over 2 times the root of 3t. Now we are ready to take dy all over dx, that is dy all over dt of 3 all over 2 times root of 3t, and this is divided by dx all over dt, which is negative 1 all over 2 times the root of t plus 1. We can cancel out 2's and get dy all over dx as negative 3 times the root of t plus 1 all over the root of 3t. Although we have a radical sign in the denominator, it wouldn't be wise to rationalize this, as later on in the application we take this as 0 anyway. Continue with the second derivative, which is started by taking the derivative of dy all over dx with respect to t. And we have negative 3 times the derivative of the root of t plus 1 all over the root of 3t. Having a ratio, we use quotient rule to have the second derivative of y with respect to dt dx. So the equation turns out having a denominator of the square of the root of 3t. The numerator uses low d high minus high d low, which is root of 3t times the derivative of root of t plus 1 minus the root of t plus 1 times the derivative of the root of 3t. In order for us to solve it more easily, let us again convert the roots with the derivatives into their exponent counterparts. No need to convert the standalone roots, as they will be simply copied later. Now we have negative 3 of the root of 3t times the derivative of the quantity t plus 1 raised to 1/2 minus the root of t plus 1 times the derivative of 3t raised to 1/2, and everything is divided by 3t. At this point, we can cancel out 3's and have negative of the root of 3t times half of the quantity t plus 1 raised to negative 1/2. And further, with the derivative of t plus 1 minus the root of t plus 1 times half of 3t raised to negative 1/2, multiplied by the derivative of 3t. Here, we take dt all over dt as 1, d all over dt of 1 as 0, and the derivative of 3t as 3. Then we transform the negative exponent as denominators, so we get the second derivative of y with respect to dt dx as the first fraction of the root of 3t all over 2 times the quantity of t plus 1 raised to 1/2 minus the second fraction of 3 times the root of t plus 1 all over 2 times the root of 3t. These are all over t. With so many denominators in the equation, we take the least common denominator to unify fractions. In this case, we take the denominator as twice of the root of 3t times the root of t plus 1. Transform each of the fractions' numerator respectively to have the root of 3t times another root of 3t minus 3 times the root of t plus 1 times another root of t plus 1. Then this big fraction is still divided by t. Although it looks complicated now, take note that the square of the root of 3t is simply 3t. Similarly, the square of the root of t plus 1 will just be t plus 1. So the equation turns out as 3t minus 3 times the quantity of t plus 1, and the new denominator turns out as 2t times the root of 3t multiplied by the root of t plus 1. Next, if we multiply 3 in the numerator with the quantity of t plus 1, we have 3t minus 3t less 3 without any groupings, where we can actually cancel out 3t minus 3t and have a simpler equation of negative 3 upon 2t times the root of 3t multiplied by the root of t plus 1. In the denominator, we also place the terms in just one radical sign, where 3t will be multiplied by t to make 3t squared, plus 3t times 1 is 3t, to have the second derivative of y with respect to dt dx as negative of negative 3 upon 2t times the root of 3t squared plus 3t. Let's rewrite the equation using radical sign to make it look simpler. At this point, we multiply everything by dt all over dx to have the second derivative of y with respect to x. We have dx all over dt solved earlier, so dt all over dx is its reciprocal, which is negative 2 times the root of t plus 1. Multiply the two terms where we can take out the 2's, giving the second derivative of y with respect to x as negative 3 times the root of t plus 1 all upon t times the root of 3t squared plus 3t. Example 3 is with the pair x is equal to t squared minus 3t and y is equal to t cubed. We work with dx all over dt as the derivative of t squared minus 3 times the derivative of t, simplified as 2t minus 3. Y is done similarly, that is the derivative of t cubed, which is 3t squared. Take dy all over dx by dividing dy all over dt with dx all over dt as 3t squared all over 2t minus 3. For the second derivative, we take d all over dt of dy all over dx. And with the quotient rule, we have the lower term 2t minus 3 times the derivative of 3t squared minus the higher term 3t squared times the derivative of 2t minus 3. Then these are divided by the square of 2t minus 3. Having this long equation, we differentiate to have the quantity of 2t minus 3 times 2t with dt all over dt minus 3t squared times 2 dt all over dt minus the derivative of 3. Take dt all over dt as 1, and the derivative of 3 is 0, to have the equation shortened as 6t times the quantity of 2t minus 3 less 6t squared, with the same denominator of the square of 2t minus 3. Then we attempt to reduce the equation by taking out the groupings by distributing 6t and have 12t squared minus 18t less 6t squared all over the square of 2t minus 3. By unifying 12t squared and negative 6t squared, we have the reduced equation of 6t squared minus 18t all over the square of 2t minus 3. Moreover, we again factor out 6t to make the equation 6t times the quantity of t minus 3 all over the square of 2t minus 3. From this point, we multiply dt all over dx to have the second derivative of y with respect to x without any dt. Earlier, we have dx all over dt as 2t minus 3. Take its reciprocal to have dt all over dx. Multiply this into the equation to have the final second derivative of y with respect to x as 6t times the quantity of t minus 3 over the cube of 2t minus 3. For example 4, we have x is equal to 1 all over t, and y is negative 2 plus ln of t. dx all over dt is the derivative of 1 all over t, which is transformed as t raised to negative 1. So by power rule, we take dx all over dt as negative 1 times t raised to negative 2 multiplied by dt all over dt, which is again 1. So dx all over dt is negative 1 over t squared. dy all over dt is the derivative of negative 2 plus the derivative of ln of t. The derivative of a constant is 0. And to take the derivative of ln t, we figure out u, which is t, and take u prime, which is 1. dy all over dt is then taken as u prime all over u, which is 1 over t. Then combine these two equations to have dy all over dx, that is, dy all over dt divided by dx all over dt, to cancel out dt's. And also, we cancel t to arrive at dy all over dx as negative t. Now take the second derivative by having another d all over dt differentiation for dy all over dx. That's negative derivative of t to have negative 1 for the second derivative of y with respect to dt dx. Since this is the reduced form for the equation, we can now work on taking dt out. So we multiply the equation by dt all over dx, where dx over dt was solved earlier as negative 1 over the square of t. So its reciprocal is negative t squared. Multiply this to the equation to have the second derivative of y with respect to x as t squared. Another example has the pair x is equal to t squared plus t and y is equal to t squared minus t. With dx over dt, we differentiate t squared plus the derivative of t. So we have dx over dt as 2t times dt all over dt with 1, which is again simplified as 2t plus 1. Do the same thing for y. So, start by differentiating the terms t squared and t, where we get 2t times dt over dt minus 1, and further reduce it as 2t minus 1. Place dy over dt divided by dx over dt to take out dt, and to come up with 2t minus 1 all over 2t plus 1. We can now proceed to the second derivative by differentiating dy over dx. And since we have a ratio, this can be differentiated using quotient rule, where we have the square of 2t plus 1 as the denominator, and the long procedure of low d high minus high d low is used for the numerator. That would be 2t plus 1 times the derivative of 2t minus 1. Then subtract the next term, 2t minus 1, times the derivative of the quantity 2t plus 1. As we have done this several times already, we can simplify the derivative of 2t as 2, and the derivative of 1 as 0. So we have twice of 2t plus 1 minus twice of 2t minus 1 all upon the square of 2t plus 1. Distribute 2 among the terms in each group to have the quantity of 4t plus 2 and 4t minus 2, then also distribute the negative sign to totally take out the parentheses. Now we have 4t plus 2 minus 4t plus 2, where the 4t's cancel out again, leaving 4 over the square of 2t plus 1. Since the equation has already been simplified, we can now multiply dt all over dx, where dx over dt was solved earlier as 2t plus 1. Take its reciprocal to have dt all over dx, and have this multiplied to the equation. Finally, the second derivative of y with respect to x is 4 over the cube of the quantity 2t plus 1. The sixth example consists of the parametric equations x is equal to 2 plus cosine t and y is equal to negative 1 plus sine of t. Once more, take the derivative of 2 and cosine t, where the first term becomes 0, and the second term comes as negative sine of t. Do the same with y to have the derivative of 1 and sine of t, which becomes 0 and cosine t, or simply cosine t for dy over dt. Divide dy over dt by dx over dt and cancel out dt, and have negative cosine of t over sine of t, which can be taken as negative of cotangent t by using trigonometric identities. For the second derivative, we take the derivative of y prime with respect to t. So that's the derivative of cotangent t, which is known as negative cosecant squared of t. Cancel out the negative signs to have cosecant squared of t. From this point, we multiply dt all over dx to take out dt's, where we found dx all over dt as negative sine of t, with the reciprocal as negative 1 over sine of t. By trigonometric identities, we can take this as negative of cosecant t. Now it is ready for multiplication. So we have the second derivative of y with respect to x as the cosecant squared of t times negative of cosecant t, which in turn makes negative of cosecant cube of t.